Conservation laws. Some physical quantities may change over time because distinct physical processes are governed by various types of forces. A noteworthy feature is that certain physical quantities may remain constant in the processes under specific circumstances. If the constraint is also mentioned, the statement is referred to as the conservation law, and the quantities that remain constant are known as conserved quantities. Therefore, a conservation law is only a statement that specifies which quantity is true regardless of the restriction. Following are a few conservation laws. Number 1. Conservation of energy. The mechanical energy of a body, the total of its kinetic and potential energy, remains constant if the force acting on it is conservative. A conservative force is one that implies that the work it does in a full round trip is zero, or that the work it does is independent of the path it travels. If the force is not conservative, the conservation of energy principle states that the total energy of the universe remains constant. This is the general law of conservation of energy. Number 2. Conservation of linear momentum. According to this, the linear momentum of a system of particles remain constant if the external force acting on the system is zero. Number 3. Conservation of angular momentum. It claims that if the system of particles experiences no external torque, its angular momentum will remain constant. These three conservation laws are fundamental laws that apply to both the macroscopic and microscopic worlds. Other conservation laws apply when we consider the microscopic realm of field. Number 4. Mass energy conservation. Einstein stated that mass and energy are not independent quantities, but that mass may be converted into energy and vice versa. The mass-energy equivalence relation is E equals mc squared, where E is energy in joules, m is mass in kilograms, and c is the speed of light in meters per second. As a result, when energy E is lost, mass m increases, and when m is lost, energy E appears. The mass of a bound system, such as a nucleus, is not exactly equal to the mass of its constituents, protons and neutrons, but is slightly less according to the equivalence relation between mass and energy. Mass defect, which is the term for the difference in mass, appears as binding energy. Mass of a bound system equals sum of masses of its constituents, which is the binding energy over c squared. Accordingly, mass of nucleus will be equal to sum of masses of nucleus, which is the binding energy over c squared. Similarly, the total number of nucleons, protons and neutrons in a nuclear reaction remains constant before and after the reaction, but the total mass of reactant nuclei and product nuclei is not constant. There is a slight difference between them, and this difference in mass appears as reaction energy. Thus, the general mass-energy conservation law states that the universe's total energy, expressed in the same unit, remains constant. Number 5. Conservation of charge. It states that the total charge of an isolated system remains constant. In addition to this, a number of other conservation laws hold for microscopic systems as in nuclear reactions.